Hi guys, I hope you're having a nice Thanksgiving break. So I thought that today we could go over chapter 9, which will be Alkyne reactions. So these are way nicer because I feel like they're a lot less picky than Alkyne reactions. But I still want you guys to remember your Alkyne reactions because they do show up a little bit more on the final than Alkyne reactions in my opinion. So let's get started. So then, introduction to alkynes. So alkynes, they're compounds that contain a carbon-carbon triple bond. Or in much nicer words, they're this. These are alkynes. Or that would be an alkyne group. So that one is sp hybridized orbital. The triple bond made of a single sigma bond and then 2 pi bonds, and then it's a 180-degree bond line angle. So then how do I know that it's sp hybridized orbital? So this is kind of like a reminder from exam 1 review. So if this doesn't really make sense to you, I would really recommend you to watch that one, because it's like a build-on basis for like everything else on this whole course. I mean, not really sp hybridization, but you're probably gonna get like 1 or 2 questions about sp hybridization. So then I think about this as number of like separate bonds. Like it can be like number of separate bonds or number of lone pairs. Like for example, we have sp, we have sp2 or sp3. So then, for example, this carbon, it has, I'm talking about number of separate bonds, so I have 1, 2 separate bonds around it, so it will be sp, since I think about it as 2 bonds or 2 circles. Let's say circles instead of bonds, 2 circles. sp2, I think about it as 1, 2, so I have 3 circles. Then here I have 1, 3, so then I think about it as 4 circles. So then, for example, something like this, it will be an sp, because I have 1, 2, 3, 4. Sorry. Something like this, it will be 1, 2, 3, 4. It will still be sp3. So something like, for example, something that can be like sp, just sp hybridized, also it can be a double bond, because I have 1 and 2 just around, like 2 separate bonds. So I have 2 circles around that, so it'll be sp. Then I have sp2, then I have sp3. So in that case, we can see that alkynes, they are sp hybridized. So by triple bond made of a single sigma bond and 2 pi bonds, I mean that the triple bond in an alkyne is made of one sigma bond, and then it's made of 2 pi bonds. And then 180-degree bond line angle, because if you visually see it, for example, you will see that there's like a 180 separation between them. So then 180 degrees represents a linear geometry. So alkane versus alkene versus alkyne. So then ethanes, methane, ethane. So ethane is a, let's see, I'm gonna put it next. So then ethane is a, ethane is a carbon-carbon. Ethylene is a double bond, and then acetylene is a triple bond, carbon-carbon. So then we know that ethane is ethane, ethylene, acetylene. If we look at ethane, we know that it's gonna be sp3, like we talked about before. Sp is 2 circles sp2 is 3 circles, and then sp4 is no sp4 sp3 is 4 circles. And how do I get that number? Because I just add 1 plus 1, then I add 1 plus 2, and then I add 1 plus 3, and that's how I got my circle number. So then sp hybridization, it focuses on the carbon that we're looking at, or the atom that we're looking at, for example. So then in that case, we're just focusing on this carbon right here. So if we're focusing on that, we're looking at number of separate bonds or circles, separate bonds or lone pairs, for example. So then I have 1, 2, 3, 4. I have 4 circles, so I have sp3. sp3, so S character. It says that we have 25% S character. So then if you look, so then sp3, so then we have 1 plus 3, we have 4, so then we have S. How much of S we have? We have 1. So then we do 1 over 4, we only have 25, so we only have 25% of S character. And normally sp3 represents a tetrahedral geometry. Also because there's no lone pairs, so then it's definitely tetrahedral geometry. And if we look at ethylene is sp2, because if we look at its number of circles of this carbon, we have 1, 2, 3 separate bonds. So then 3 is for sp2, so this one is sp2. It will be the same for this one, it's sp2. And again, how do I know how much S character does it have? So I do 1 plus 2, I have 3. So then how much of S? I only have 1 over 3. I have 33% of S character. And normally sp2s, no lone pairs, no anything, they show a trigonal planar geometry. And then acetylene, which is what our chapter is about, is carbon-carbon triple bond. So that one is sp, as we mentioned. You have, you have this one and 2 circles around it. So I only have 2 circles, so then I have sp. So then again, how much S character do you have? 1 plus 1, I have 2. How much of S I have? I have 1 over 2. I have 50% of S character. And we said that an SP normally represents a linear geometry. And again, and if you don't, hopefully this made sense for the people that do remember a little bit for geometry, about linear geometry, tetrahedral, trigonal planar. They remember sp2 and sp3. And if not, you're not late. Just go watch the exam 1 review, and I promise it's gonna be really helpful. If not, you can always email me and we can go through it. So then we have nomenclature of alkynes. Yeah, not again. IUPAC rules. So then the good thing is that we can use the same steps, remember them. So step 1, as we know, is identify and name the parent. The parent chain is going to be your longest chain. Second step, identify and name the substituents. Substituents are the things that are hanging from that parent chain. Number the parent chain and assign a location to each substituent, meaning assign a number to each carbon of the parent chain. And then after that, assemble your substituents alphabetically. But there's some rules for alkynes. So then alkyne, your parent alkyne, is gonna have a suffix of alkene. So then, for example, if you had no triple bonds, just a regular like carbon single bond, you can see that it ends in pentane, like your parent chain is named pentane. If your parent chain contains a double bond, it's gonna be pentene. And now in this case, if your parent chain contains a triple bond, it's gonna end in pentane. So then the parent chain is the alkyne, is the longest chain that includes the carbon-carbon triple bond. So then in this case, for example, we have 1, 2, 3, 4, 5, 6, 7, 8, right? But in here we have 1, 2, 3, 4, 5, 6, 7. So the thing is that this one will end up being your parent chain, because the thing is that we know that parent chain normally is the longest chain, and you'll be like, oh, then why we didn't pick the one with the 8 carbons? Well, the thing is that we want the one that includes the triple bond, because a triple bond has higher priority. So then we want the longest chain that includes that higher priority group. So considering that, the longest chain that contains that group is gonna be that 7 carbon subsequential chain. So when assigning the number of carbons to each substituent of our parent chain, the triple bond should receive the lowest number possible despite the presence of an alkyl substituent. Meaning, for example, we don't really care when normally alkynes, they have higher priorities than other groups. Like in this case, at least, alkyne has a higher priority group, therefore we wanted to have like the lowest number possible. We don't care about other substituents, we care about that alkyne to have the lowest number possible. That's why we start counting from this side rather than start counting from the other side. So like I said, that one will be the correct way. So then, position of triple bonds is shown using a single number of carbons, not 2. Considering that the triple bond is between carbon 2 and 3 and the parent chain, the position of the triple bond is indicated on carbon number 2. Like you can see that let me highlight our parent chain. And these ones are my substituents, as you can see. So then normally when we have something like double bond or a triple bond on our parent chain, we normally want to indicate where is that, or where does that double bond or triple bond starts. So you can see that we have a bond between 2 and 3, right? So we're just gonna indicate that triple bond starts at carbon 2. We're not gonna say that it ends at 3, we just say that it starts at 2. And it says or because the rules are so weird that there's no, like, you can name it this way or this way, either will be correct. So you can put the position before you say your parent chain name, and you can put it between the parent chain name. I personally prefer to put it before, but it's up to you guys. And of course, on a test, I think you'll be able, as long as you know your substituent positions, you know how many substituents you have, you alphabetize them correctly, and you know where your alkyne starts or your alkane starts, and that you put the correct suffix, then you should be good. So some common names. So ethene is a carbon-carbon triple bond. A carbon-carbon triple bond is called an acetylene. So this is an acetylene technically. So then sometimes you're gonna see things like methyl acetylene, like this is the methyl group, diisopropyl acetylene, and then diisopropyl, and then phenylpropyl acetylene. So here's some terms. So then we have terminal versus internal alkenes. So a terminal alkyne is a monosubstituted acetylene, while an internal alkyne is a disubstituted acetylene. So terminal, you can think about it this way. Terminal, you know, it's just gonna be monosubstituted, an alkyne. Well, internal, you know, it's between two carbon internal in between, disubstituted. So now let's practice. We haven't done a practice problem in a while. So then provide a systematic name for the following compound. I mean, you can always try it on your own, and then, but you can always try it on your own and just pause me. But if you want to see me first solve it, and then you can try the next one, then that could work as well. Okay, so we just have to find the longest chain. And remember, it has to be the longest chain that includes that triple bond. So then let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, perfect. So I feel like that one should be our longest chain. That includes that triple bond at least. So in here I have a metal. In here I have a metal. I have 1, 2, methyl, ethyl. I have an ethyl. Then remember, we want our, when we're numbering, we want our alkyne to have the smallest number possible. So we might want to start counting from this way. So we have 1, 2, 3, 4 sets. Okay, perfect. Now we have this. So our longest chain, it will be called so normally if it didn't have any triple bonds, it will be decane. But since we have triple bonds, it's gonna be called decene. Decene, because we have to add that suffix, so we know our parent chain name. Okay, so we have to just organize them alphabetically. So then ethyl is gonna go before methyl. So then we have 5 ethyl. And then I have 2 methyls on carbon number 7. So I'm gonna put 7,7. And then I have 2 methyls, so I'm gonna put dimethyl. And then where does my triple bond start? It starts at number 3, and it's gonna be decene. So that will be my answer for that one. Okay, so now you can try it on your own. So that one's pretty easy, since you don't really have to think about it too much. Your longest chain, you can start from this way, or you can start from this way. You will still get the same thing. Yeah, I wanted to be nice with you guys this time. So then let's see. You have 1, 2, 1, 2, 3. So then I can start counting either way. I have 1, 2, 3, 4, 5, 6. Like, I could have started counting from this way, but since our alkyne, like, it will get like 1, 2, 3. Then now we have to consider the fact that our substituent, this one, it will get a lower number. Then that's when we actually care. So then we want also our substituent to have the lowest number possible as well. So then if we debate between a 1, 2, or like a 1, 2, 3, 4, 5, we will prefer to have a 2/5. So we'll start counting this way. So then in here we have a metal. So if it didn't have a triple bond, it will be called a hexane, but since it has a triple bond, it's gonna be called a hexene. And luckily we only have one substituent, so we're gonna have 2 metal. And then we have to say where does our triple bond start, which is gonna be 3 hexene. And that's gonna be our answer. Okay, acidity of acetylene and terminal alkynes. So remember, Ario is atom resonance induction and orbital. Orbitals showed us that sp are more acidic than sp2s and are way more acidic than sp3s. This concludes that a triple bond carbon-carbon is more more acidic than a single carbon-carbon. And we can see it in here in our pKa tables. We can see that a triple bond carbon-carbon is more acidic than a single bond carbon-carbon. So then, yeah, we have to remember these terms. Don't worry, I have to look back. I have to look back on them too. And I probably should take a picture because I'm probably gonna forget. So I think that would be a nice idea. So then we have Bronsted-Lowry acid. So then Bronsted-Lowry acid is a proton donor. Bronsted-Lowry base is a proton hydrogen acceptor. A Lewis acid is an electron pair lumper acceptor, and a Lewis base is an electron pair lumper donor. This will make sense after we do some problems, but keep this in mind. So then if I have a weak base, I have a strong acid, and if I have a strong base, I have a weak acid. Equilibrium always goes to the weakest side, and Ario winner, the one that we say that wins an Ario, it's the weak base, strong acid. If in one side is a weak base, on the other side it's gonna be a strong acid. So then Ario is my favorite topic. So then a summary. So then, like we said, the winner shows the strongest acid or weakest base. So then Ario, A stands for atom, and basically it's where is that negative charge located at. So we have 2 compounds. One has an oxygen negative and the other one has a carbon negative. Then our Ario winner is going to be the one with the oxygen negative. Resonance, how many resonance structures, the more the better. So the more resonance structures it has, the more acidic it's going to be, or the more acidic it's going to be. Induction, how many induction factors or molecule has, like how many chlorines, bromines, iodines, fluorines, the more the better. So then I remember doing this kind of problem with someone. So then I have this. So then in here I have like you can see I have 1, 2, 3 induction factors, and then in here I have only 1. So the one that has more induction factors is gonna be better. So then this one's gonna be my Ario winner. So that's induction factors. And then I have my orbital. So like we said, sp is better than sp2 than sp3. And then another factor that is not really mentioned is that the less bulky your structure, the better. So the less bulky it is, like if you have a structure that they're similar on everything on aerial terms, most of the time it's gonna be because the most acidic is gonna be the less bulkier. So then let's practice. So then using what we know about aerial, determine whether sodium acetate CH3CO2Na is a strong enough base to deprotonate the following terminal alkyne. Okay, so basically this is how it's gonna go. Let me put this one up. Okay. I'm so sorry if this is gonna look really ugly. But at least you're gonna learn aerial with me, which is nice. It took me a while to actually learn to like aerial. I hated it at the beginning, but I feel like it's quite rewarding, like knowing which is more acidic or not. But maybe that's me. But I prefer doing this over Newman, to be honest. Okay, so I stopped because I first want to see what the problem want us to do. So I was asking if this is a strong enough base to deprotonate the following alkyne. Deprotonate, it means that it's going to take a hydrogen from it. So we're going to see if this one is strong enough to take a hydrogen from it. So then technically they want our product to be something like this. Okay. So then let's see, we have to determine which ones are base and are acid. So then we have to determine which is my base and my acid. So then this one is gonna be my base and this one's gonna be my acid. So then my base is normally, we're gonna use that Bronsted-Lowry term. So my base is gonna be a proton or like a hydrogen acceptor, while my acid is a proton donor, like it donates. You can see that our hydrogen leaves because our base is taking it from it. So then I have my acid. So then here I have my acid, right? So then this one is like the same, or like the similar molecule to it, but instead on the other side it's gonna be called my conjugate base. Therefore this on the so then on the other side my base is gonna be called a conjugate acid. So then now we can compare bases, and that is when aerial comes into play. And that's how we're gonna determine if it's strong enough to deprotonate it. So then I have my aerial. This one's pretty easy because in here you can see we have atom. Atom stands for where is that negative charge located. My negative charge, I have it in an oxygen negative. Well, in here I have my carbon negative. So we know that it goes CNOF on the periodic table. So then oxygen is gonna be more reactive than carbon. So then therefore this one's gonna be my winner in aerial terms. Okay, so then if I have that, so then that means, remember that area winner means it's a strong acid, weak base. So then that's what I meant about like weak. We have a weak base, strong acid, and strong acid, weak base. So then my winner is gonna be a weak base. So this is my winner, so this one's a weak base. So then it's similar on the other side, is a strong acid. Well, my loser is a weak acid. And it's gonna be, therefore, it's gonna be a strong base. Considering that, remember equilibrium, it goes to the weaker side. So my equilibrium is gonna go this way. Meaning that the reaction is gonna go this way instead of going this way. So then that means that that sodium acetate, this wasn't strong enough to deprotonate a terminal alkyne, because what they want ultimately is that the equilibrium to prefer this side to go this way. But since we did our area and we analyzed the reaction, we were able to see that equilibrium didn't want it and it went this way. So then that means that sodium acetate wasn't strong enough to deprotonate that one. Now it's your turn. Good luck. Okay, that's not really mean. I think you can do it though. Okay, perfect. So then let's see. So I will tell you to just write your reaction. Oops. I don't know how many times you have heard me say that. Oops. Like on all these like videos, I don't know how many times you heard me say that. Okay, so it's asking if this is strong enough to deprotonate it. So we're gonna be taking a hydrogen from this side. Let's see. And here I have a carbon, so then I don't want to see that. Let's see. Okay, perfect. Okay, so I have to determine which is my base and which is my acid. So then remember, my base is gonna take a hydrogen. So then this is my base, this is my acid. So then remember what we said, my acid, if I have my acid, that similar structure that looks like it on the other side is gonna be a conjugate base. And the same goes for my base. My base on the other side is gonna be a conjugate acid. So then now in terms of aerial, we can look at our bases and compare them. So then lucky enough, this one is the same thing as well. Let's see. Strong enough base to the proton in a terminal alkyne. Then I have N negative. I have this one. And then I have here, I have a carbon negative. Okay, let's see this side is strong enough. I'm gonna take from it. We have this one, we have negative Na plus. The carbon, the nitrogen, CnH2. Oh, okay. Okay, so then here's the cut. So then for things like this ones, most of the time they're gonna give you guys pKa values, because I was about to use area and say, you know, that negative nitrogen, you know, it's gonna be technically our area winner because it goes from CNOF. Therefore, this one will be our weak base. So then, you know, on the other side, then it wouldn't. But the thing is that things like CNH negative, or they're really unstable. So then, therefore, they make like strong bases because they really need a proton. They're strong bases, they really need a proton. So then, the thing is that this would apply aerial to everything else. Like for example, if my nitrogen had like if this nitrogen had like a carbon in between them, then it had been really helpful. Then it would have been true for this problem that our equilibrium will go this way. But then since it only have hydrogen surrounding it, it has a pKa of 38. Well, this one has a pKa of 25. So then, thinking of pKa values, if we look at pKa values, pKa at the same, it says that this one's gonna be so then this one is a stronger acid. This is stronger acid, weak base. And then this points that this is a weaker, at least compared to the two of them. If we compare 38 to 25, this one's gonna be a weaker acid. So then if we think about those terms, then let's see if I have my acid in here. My acid, this one will be weak. And this one's gonna be a strong base. And for this pKa, it's gonna be a weak base. And then this one's a strong acid. So then my equilibrium, remember, my equilibrium goes to the weaker side, so then it's gonna go this way. Therefore, that means that this is strong enough to deprotonate my alkyne. Okay, so we can get to some reactions. So preparation of alkynes. So alkenes can be prepared from alkyl halides. And alkynes can be prepared from alkyl halides. So remember, we only, to prepare an alkene, we just needed like one halogen. So to prepare alkynes, we need two. We need a dihalide. So just a heads up, it doesn't matter if like your second halide is in here or if it's in here like it's shown. It doesn't really matter. As long as you have a dihalide and you have a strong base, then you can create a triple bond. So the mechanism. So then an alkyl halide has two leaving groups, therefore the reaction can be achieved by doing two elimination reactions. So then how does it work? So then remember, bases, they take hydrogens, which then create, this one, it creates a negative charge, which then we have one leaving group, we have a positive, then we create a double bond. We have a double bond in here, then we repeat the same. We take a hydrogen, which goes in here, we do a negative charge, and then in here we have a leaving group, which goes positive. Then we can create, between that negative and positive, we can create another bond, and then we get our triple bonds. Or basically, if you have a strong base and you have two halides, you can create a triple bond. And you can see here, like in this case, we have our carbon in here, and we have a dihalide, right? On this one previously shown, we have a dihalide. We have our halides on the same carbon. In here we have it on different carbons. As long as they're next to each other, then you can create a triple bond. So then NH2 or sodium amide dissolved in liquid ammonia, NH3. This method is used to prepare alkynes, triple bonds. You can see we have two equivalent of NaNH2, which kind of makes sense because due to the mechanism, we do elimination 2 times, so we need 2 equivalents of this base. Once we have our triple bond, we can again use NaNH2 to create an alkynide ion. So like we said, if we begin with an alkyl halide, this is an alkyl halide, and with just 2 equivalents, we can create an alkyne, and we can do an extra equivalent, or in total 3 equivalents, if we want an alkynide ion. So then something to take into account. Sometimes there will be a number shown, like in here, or it would just shown like this, like excess. So then I just wanted to show you guys that there's different ways of writing reactions. Like for example, oops. Okay, we're still recording, okay. Let's see, let me open this one. I just want you guys to be able to see that they can be graded. We have different ways of writing reactions, and we still have our D halide. We still use this one as excess, and then we are still able to get our alkyne. So then, conceptual concept. For each of the following transformations, predict a major product. Conceptual concepts, so you can pause me and give it a try. So technically, I mean, I can draw the mechanism for you guys, like. So then it's gonna technically be like a base. It's gonna take a pattern, and at the same time we're gonna have a leaving group simultaneously. And then this one is gonna go on to create like a double bond. And then again, since we have excess, we can do the same reaction again. This one's gonna take a pattern from it. We can create a triple bond, then this one leaves. Which will give rise to this product technically. And this one will be my answer. So you don't really need to draw the mechanism, but I do want you guys to understand how we went from this side to that other side. Because sometimes I feel like it's not really gonna be like really obvious. So then I do prefer to draw the mechanism sometimes. But it's up to you. So if you're able to actually like visualize the product, then you can do whatever feels better for you. So in here we have like our highlights not on the same carbon, and you can see that we can still gonna be able to get the same product. Let's see, let me restart for a second, because that one wouldn't really make sense. So then let me use this. Okay, perfect. That always makes sense. So then that one will be my answer right there. 1, 2, 3. That will be my final answer for this one. So catalytic hydrogenation of H2PT. So remember that alkynes can also undergo catalytic hydrogenation. Like remember we use H2PT to go from an alkene to an alkane. So we can do the same. You can use an alkyne and then just with H2PT, you can convert it completely to an alkane. So the thing in this chapter is that we're gonna put things in brackets. This is kind of like an intermediate. So this is not like our final product. Like our final product, it will be this one. So wording, alkyne with H2PT leads to formation of alkane. There's no alkane product. Like we mentioned, it's just an intermediate. It's not our final product. So in order to get an alkene, we need a Poise catalyst. Notice the product is cis alkene, no trans alkene. So then with Poise catalyst, we have Lindlar catalyst or an Ni2B. So then if we have an alkyne and we use H2 Poisson catalyst, we get a cis alkene. We don't get a trans. We don't get a trans alkene. So let's practice. Let's draw some major products. So then we said that when we do a Lindlar's, we get cis, right? So if we get this, we get a cis alkene. But if we use this, we get an alkane, right? So then since they want an alkene and they want it to be cis, you can just draw it in this way. Since cis means that they're going to be pointing on the same direction. And then H2PT, so then it's technically like we're just gonna try to draw it without the triple bond. So if it's a little bit hard for you to visualize, so you can just count the number of carbons you have, so you can make sure that you did it correctly. So you have 1, 2, 3, 4, 5, and here I have 1, 2, 3, 4, 5, and then I have 1 carbon pointing up on my second carbon. So then I have 5, 1, 2, 3, 4, 5, 6 carbons. I have 6 carbons, so then I should be good. Okay, so now you can try it on your own. Okay, so we said that an example of a Poisson catalyst, it can be Lindlar's or Ni2B. So then this is an example of a Poise catalyst. So then we're gonna get a cis alkene. Well, in here, H2Ni, you can use things like PT, PD, or Ni. So then I would just get an alkane. So from our alkane side, 1, 2, 3, 4, 1, 2, 3, 4. And then I have 1, 2, 3, 4 in here. And then an alkene. So then what I do when I have alkenes and they want it to be cis, have 1 pointing down and then have 1 pointing down in here. And that one will be my answer. So then dissolving metal reduction NaNH3. So then when we reacted with this, with NaNH3 liquid, we go from our alkyne to a trans alkene. So that's basically it. So then draw the major product expected when each of the following alkynes is treated with sodium metal liquid ammonia. And I felt like this one was really straightforward. We're just gonna draw our trans alkene. Our trans means that they're gonna be in opposite directions. You can see this one's pointing down, this one's pointing up. I better let's practice. You also try it on your own. So then you can try it on your own now. Oh, that looks ugly. So you just try it on your own. Okay, nah, I'm terrible at drawing apparently, at least on here. So then let's see, let's draw a major product. I'm sorry. Let's see. So then we have when we react with a sodium or NaNH3, remember this is gonna lead us to a transalkene. One, two, three. 1, 2, 3. So then again, if you're not really sure, you can use your number of carbons to make sure you're correct. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, perfect. I think we got it. So summary. So alkyne that reacts with H2PT just by itself, we get an alkane. Alkyne with H2 with Lindlar catalyst, you get a cis alkene. And then an alkyne with NaNH3, you get a transalkene. And if you react any of this cis or transalkene with H2PT, you get an alkane. So this is kind of like for us visual learners, or I think it's pretty nice sometimes to get something in a chart just by looking at it visually. So if this one helps, I think it is very helpful. So then let's practice. Identify the reagents that you could use to achieve each of the following reactions. Okay, so let's practice. Identify the reagents. You can use this one. Okay, so we have this one. We go from here, and then this one seems like a cis alkene, right? And then this one seems like it's trans alkene. So then for a cis alkene, so H2PT by itself, we just get an alkane. If we do with H2 with poised catalyst like Lindlar's or how's it called? Na2B, then we get a cis alkene, right? So then we can do that. We can use H2 Lindlar's. And then for a transalkene is like the previous example we did before. We used NaNH3 liquid, right? So you can think about it this way, like look at your starting material and look at your final material and look, how did I go from here to here? Okay, so try it on your own. Identify the reagents that you can use to achieve each of the following transformations. So then let's look at our final products. And here we have a transalkene, and then in here we just have a regular alkane. So this one's pretty easy, right? H2PT, or it can be PD or Ni. Then transalkene, we have Na, and then we can use NH3 liquid. Okay, hydrohalogenation of alkynes. So similar to alkenes, Marconic of addition is observed when alkynes are treated with HS, addition of hydrogen and halide across a triple bond. The same rules, halogen goes to the more substituted position. So then I put as an example in here, just like a little reminder what we did with alkenes. So with alkynes, basically we do the same thing. We are adding like if we get one equivalent, we are adding our halogen on the more substituted side. And then we're adding our hydrogen to the least substituted side. Some things to consider, but if we want to create an alkane instead of one equivalent of HS, we need excess HS. And then we're gonna be adding those halogens on the same carbon, unlike on the more substituted side. The two halogens are added to the same carbon position, the more substituted side. So then hydrohalogenation of alkynes. This is technically what happens when you get excess. This is what happens when you get one equivalent. This is a thermomolecular reaction. Like we said, it's a Markovnikov reaction. We're adding the halogen to the more substituted side. If excess, the two halogens are on the same carbon. And the rate for this reaction is K times alkyne times HS squared. So then I personally haven't really gotten any problems relating to the rate of this reaction, but I think it's nice to know because you never know when you're gonna need it. If you want it like more nicely, then just like gooding out like that, because I couldn't copy paste that from the book. It was kind of like this. But just remember that this is the rate for this reaction, and it's going to be thermomolecular. And I believe it's thermomolecular just because remember that on SN2s they were bimolecular, because we have like two things happening at once, and here we have like three things happening at once. Because in here, like if you look at this, we have a leaving group in here. One, we're doing a proton transfer, then the second step. Then in here, that other halogen is also like adding to it. So it's kind of like technically we're adding one, the one it's leaving, which is later gonna attack it. So then we're doing like three things at once. So that one is thermomolecular. So yeah, so at least for this, I feel like they didn't provide any examples from the book, but at least you know that you're familiar with HS. So when dealing with alkynes, remember to just put it on the more substituted side. And if you get excess, remember to just add 2. Just reduce it completely to an alkane, but then you're gonna have to add two halides to remove that triple bond. So then remember ROR peroxides. They can be used for alkynes as well. This reaction would proceed through anti-Markovnikov addition, creating a mixture of E and C isomers. So then if we use HBr ROR, notice that at the end end we're gonna add our bromine or our halogen. We're gonna add it at the end, but our product is gonna be a mixture between between trans and cis, so we're gonna get a combination of products. So interconversion of dihalides and alkynes. So that's kind of like a chart. Like remember, if you get an excess of HS, your halogens are gonna go to the more substituted side, which will be this one. And then if you want to like reduce it, remember NH2 is a base is a proton. It's like a proton acceptor, it takes protons from it. This one has a proton, it's gonna take away from it. Therefore, like from here at least, it's gonna take from it, which is then you have your leaving group, then you're gonna be creating a double bond, then you're gonna repeat that, you're gonna do the same thing again, and you're gonna do a triple bond with it. So then let's practice. Okay, so then like we said, things like Na, NH2, NH3, this one is a strong base, it's gonna take protons from it. It's gonna take protons away, so here you have hydrogen, hydrogen, hydrogen. And we have excess, remember, so then we're gonna fully create a triple bond. We're gonna remove it in here. This one's gonna create a double bond. This one leaves. And then again, we're gonna do it all over again. This is a 2-step, so then again, we're gonna remove one. We're gonna create a triple bond from that. And then we're gonna remove this. So then for these steps, this one are kind of like one step together. We're gonna get something like this. 1, 2, 3. Okay, and then I'm gonna have my HBr, ROR. So then remember we said that this was anti-Markovnikov. Since this one's anti-Markov, I will add up bromine to this side, right? But it will be a mixture of products in this case. So then remember, I will get a cis and then a trans as well, or trans being the major product. Okay, so excess HBr. So in this case, let's see. Or BR, it will go to the more substituted side. And if you really wanted to like visually see the mechanism, it's technically the same thing as when we did with our alkenes. Let's see, let me see. I had breathe this right. Oops. I was worried about the space. Okay, let's see. I don't really remember it that well, but let me see if I can. Let's see if I have carbon in here. Hydrogen. See, this one's some more substituted positive. I'll get my carbon here, hydrogen. My hydrogen will go this side. We're technically breaking that triple bond. So then our bromine is all by itself. That bromine that left, technically we get a bromine in here. For negative bromine, it's gonna attack this side and then we will repeat it. We will repeat the same action. HBr. This one's gonna take from it, this one takes from it. I'll get something like this, a positive. Then I'll get Br in here. I get a positive on one side, and then my hydrogen is added to the side that's step substituted. Then I have a hanger Br that it can do a nucleophilic attack. Oops. So then my final answer, it will have to be something like this. No, darn it. Okay, so then let's see, let me erase that. Okay, let's see. 1, 2, 3. 1, 2. One, 2, 3. 1, 2, 3. One, 2, 3. One, 2, 3. Okay. And that should be my answer technically. So what I want you to see is that it's basically this. I know that I did like a whole mess, but I wanted you guys to see how the mechanism worked technically. Since technically like that triple bond is gonna take a hydrogen from it, or hydrogen is gonna go to the less substituted side. Therefore, on the more substituted side, we will end up with a positive charge, which then that bromine, you see that we took a hydrogen from that bromine is gonna attack that positive charge. And like we know, or a diene overall, or both of our halides, they're gonna go on the more substituted side. So then you can try it on your own. Okay, this is pretty nice. Since we did the first step together. Okay, let's see. So it is nice to think about, like, this one is a strong base, So then it's gonna take hydrogens from it. Therefore, it's gonna leave, and then we're gonna create a triple bond from that. So then this is a whole reaction together. So then we have this as our next step, which is excess hydrogen bromine, and then we know that we're gonna be adding our bromines. Since we have excess, we have 2 bromines that are gonna be added on the more substituted side. Okay, so then let's see. Okay, this is the same logic as the one up there. And then again, we know NH2 is a strong base. Let's see here. Let's see, here I have strong base right here. Therefore, I'm just gonna create a triple bond from that. So I have 1, 2. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, perfect. And I would end up with something like this. Okay, hydration of alkynes. So we have acid catalyzed hydration of internal alkynes. Will give a product of a mixture of ketones. So then, one thing that you have to take account into this is that if we use this, if our alkyne is not terminal, then we're gonna get a mixture of ketones. Like, we're gonna add a ketone to this we're gonna do a ketone with this carbon, and then we're gonna do a ketone with this other carbon. Like you can see it in here. We did a ketone with the carbon on the left, and then one with the carbon on the right. But then if our alkyne is terminal, then we're just gonna generate a ketone as the product. And it's gonna, so then we are gonna create a ketone, but just not with the one that's terminal. So then just with this one. Okay, let's practice. So then draw the major products expected when we get the following. Alkyne is treated with aqueous acetate and the presence of mercury sulfate. So like you said, we're gonna create ketones. So I'm gonna create a ketone with this carbon and then with this other carbon. So we get 2 products. So then here I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll get 1, 2, 3, 1, 2, 3. Okay, so then here I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 2, 3. Okay, perfect. And that will be my answer. So isn't it really that bad? Okay, so I was a little mean. So then remember, this one's terminal. So we're not gonna get two products, we're gonna get just one product. And remember, it's not gonna be, we're not gonna make a ketone with this side. Let's see. We're not gonna make a ketone with this side, we're gonna make a ketone with this side. Thinking about that, that one will be my answer right here. Okay, so hydroboration, oxidation of alkynes. When there's this reaction, our initial product is an enol. But this is not the final product. It's an intermediate, so which is instantly converted into an aldehyde. So the mechanism, it is kind of difficult. So this is more of organic chemistry 2 stuff, so it's not really required for OChem 1. But then we're gonna be creating an aldehyde. An aldehyde is this. So then you know this is a ketone, an RR. So then when we have an R and then a OH, this is gonna be an aldehyde. So hydroboration, when we get this, it's gonna create an aldehyde. And you can see that when it's terminal, like we're gonna be creating a ketone, like a ketone technically, but then since we have a hydrogen next to it, we are technically creating an aldehyde. So how does that work? So then technically hydroboration, we're gonna be adding an OH group to the least substituted side. So then if we observe this, the enol from here, that OH that we have in here is in here. It takes a proton from it, which goes in with that broken bond, it becomes a lumper and that oxygen. Then in here we can do resonance structures, creating a double bond on that oxygen, and then we're gonna be breaking that double bond next to it, so then we don't break any octet rules. And since we have a negative carbon, we can always take an extra hydrogen if we wanted to. So that's how we end up with an aldehyde. So it's like I said, it's not really a requirement, but it's for you to know how does it work. If not, just take that in mind that when we do hydroboration, we're technically doing an aldehyde. We're creating an aldehyde from it. So then you have to think about it. So then an aldehyde is a group that have an oxygen with a hydrogen, right? So then what looks more similar to it is this side than this side, right? So here we're just gonna add an O group, like our double bonded oxygen to this side. So just take into account that we just have one product on that side, and we don't have two. So for hydroboration of alkynes, most of the time BH3 is not used. Instead, we use things like dimethylborane or 9-BBN. So basically, they're like, you can get BH3, THF, but you can also things like this semialborane and 9-BBN, just like in here. Like you can see, they just added an oxygen in here and they broke those double bonds. They broke that triple bond and converted to single bonds, and then they added that ketone group and creating an aldehyde with this group. We still did the same reaction, it's just that on top it says diethylborane. So then we're gonna do our major products right now. So we're gonna be breaking triple bonds, we're gonna convert it to a single bond, and we're gonna add a ketone, creating an aldehyde, right? So then let's see, I have this. I just want it to look nicer. Let's see, here I have a hydrogen, 1, 2, 3, 4. And that one will be my answer for this one. So you can try it on your own. So like I said, 9 BBN or BH3, they're the same, so don't overwhelm yourself. We're just gonna be creating an aldehyde. Okay, perfect. Taking that into account, we're just gonna be converting that triple bond to single bond. And then we're gonna be creating a ketone, right? And this will be our final answer for this one. So halogenation of alkynes. So if we add one equivalent of x squared, x2, we get two products, a dihalide, which our product is going to be trans and cis. Trans product is going to be our major product. So then remember when we did alkenes, when we got like chlorine, bromine, we were gonna end up like adding across a double bond. We added on one side a chlorine and then the other side a chlorine. In this case it's the same, but since we're doing alkynes, you know, it's gonna, if we only have one equivalent of S square, it was gonna go from alkyne to alkene. So alkenes, they can only do trans and cis, meaning that we're gonna get two products, trans and cis, and trans is gonna be our major product. So we're still adding those halogens across the double bond. It's just gonna be trans and cis. But if we have two equivalent or excess, we just have a tetrahalide, and we don't care about stereochemistry by then. So as analysis, I know it was one of our favorites. It was one of our favorites on alkenes because they were, I felt like they were kind of fun, and I feel like it was easier. We just have to erase bonds. In this case, we cannot do that. When treated with ozone, alkynes produce carboxylic acids. I mean, if you wanted to, but the thing is that, we are breaking, but we're gonna do a double bonding here, and we're gonna be creating an carboxylic acid, and in here we're gonna break it in here, and we're gonna create a carboxylic acid, and that's how. But keep in mind, this is an in-between alkyne. If it's terminal, we are still gonna get on one side a carboxylic acid, but on the other side we're gonna get a carbon dioxide. So keep that in mind. So then let's practice. Okay, perfect. So if it's in between, if you really miss your eraser method, I guess we can do that. So this will be our answer. Since it's in between, we can create two carboxylic acids. But in here, down here, it's terminal. So then on one side, remember what we said, we are gonna still create our carboxylic acid, but on the other side, we're gonna create a carbon dioxide. So then, like we said, we're gonna do a carbon dioxide on one side, and then on that other side, we're gonna have an carboxylic acid. Okay, perfect. So you can try it on your own. Okay, so again, you can do the eraser method if you wanted to. I mean, I also want to. But let's see. In here we have, we're gonna create a carboxylic acid. And then in here, we're gonna create a carboxylic acid. And that will be my final answer. So alkylation of terminal alkynes. So this is one of my favorite reactions. So then remember that NaNH2 is strong enough to deprotonate and take a hydrogen away from a terminal alkyne. So then by doing that, we can add an extra step. Like, this is what I mean by extra step. We can do a step number 2. And then we can do an SN2 reaction. Remember, SN2 is substitution. So then therefore, this is going to leave. And this one can act as a nucleophile. So then, SN2 reaction, we can add an alkyl group on the deprotonated side, and this is called alkylation. Okay, so here we're gonna go over the reaction. So we're gonna try to go from here to here. Okay, so then in here we have NH2 negative. Remember, Na is a net spectator, so we don't really care. So bases, they normally take protons, right? So then this is gonna take from it. Sorry. Let's see, this is gonna take away from it. Unbelievable, me, I got that one wrong. Okay, so that makes a lot of sense. I was like, huh, how are we gonna do this? Okay. It was one of my favorite ones, I remember. It's just been a while. So then, okay. So then you can see here, our base, it took our hydrogen away from it. Then that's why we have a carbon negative. And then we have our second step. So the thing is that this carbon is gonna attack this other carbon, and then this is gonna cause this one to leave. So then that's how we get this product, because it attacks it. And then now we add that carbon to it. So we have this one carbon, and then we have, like, we're creating a new bond between these two. And it's kind of like it becomes one. So that's why I like it, because it's fun. It's fun to see how it changes. And also I feel like it's a really basic reaction, you know, because NH2 just removes a proton from it, and then you just do like a nucleophilic attack. and then you just add a new alkyl group to it. So I feel like that one's pretty fun. Okay, let's see. So let's practice. So starting with acetylene. So acetylene is this. It's like a carbon-carbon triple bond. So then they want us to go from that to 2-hexene. And 2-hexene is normally like represented like this. So they want us to show what we will use to prepare this compound. So I have an added metal group to this one. Let's see. 1, 2, 3. Okay, so it's gonna be like a 1, 2, 3, and 4 step. So then if you see here, we start from here and we end with 2 different groups, right? So then we're gonna start with our deprotonation. We're gonna start with NaNH2. And then our third step is also gonna be NaNH2. So then it doesn't really matter what order. So then the thing is that since we're starting from acetylene, our base is gonna take away from here. Just like we saw on the mechanism that we did. Gonna take away from it. So we need something. We need a leaving group. It can be anything. It can be a bromine or an iodine. So then, for example, if we wanted to add this to the side that we're taking away, if we're adding that to the side we're taking away, we have a metal. We have a metal group in here. It's gonna be a kind of like a line. It's gonna be a bromine. So then our negative, it can then, attack this side, this carbon in here, and then this one leaves. So then we would end up with something like this. And then on step number 3, it's gonna take away from this. And then we're gonna have something. We want this group on it now. So then we have 1, 2, 3. We have 3 carbons. So then we have 1, 2, 3. So then this one in here is gonna be able to attack this one leaves, and that's how we technically get this one. So it's kind of like a synthesis problem. You're gonna have to think about what things can you use. But I feel that's why it's one of my favorite reactions, because there's so many ways you can actually, like, I arranged it in this order, but it could have been a different order. Like, for example, I could have used this one first and then use that other one second. since it's a synthesis problem. So let's see, 2,7-dimethylfuranoctene. So then I think it looks like this. If I'm not wrong, I think it looks like that. So then they want to go from here to here. So then they're asking us what we need. So then, as we know, we're gonna need our NaNH2, right? So then, for example, if I were to take it from this side, and let's say I would want this one in here. So I would need a bromine. Of course, I need a leaving group. But then I need 1, 2, 3. So then I have 1, 2, 3. So then, you know, it can later attack it. And then this one can leave. Okay, so after that, we have installed this group. And now we need to install this group. So then we need an NaNH2 again to remove this hydrogen from this side. And then we want to add this side as well. So 1, 2, 3, 1, 2, 3. And then I add my leaving group, and that's how I was able to get that set. Then try it on your own. 1-hexene. Let's see, so then 1-hexene is gonna look like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So then here I have a hydrogen at the end. So then remember that we are starting with an acetylene. We know that acetylene is just like this. And technically we just have to do two steps. We don't have to do like 4 steps. So then basically we can use NH2. And then they want us to add this group. It's composed of 1, 2, 3, 4. So we're gonna have 1, 2, 3, 4. Then we have our leaving group, right? So then we use NaNH2 to remove a hydrogen from this side. And then we use this group to install this alkene to this side. And then we don't really need to do another step because it's not really asking us to add another alkyl group. Okay, perfect. So I think those are all the reactions that we have to go over for this chapter. So then we have a small summary, like at least like a visual summary. So if it's useful for you, you can always screenshot this page. And I'm just gonna do like a small summary like I did on the, like I know I did a separate video for alkynes. I did a separate video, but I feel like there's not that many reactions. I think there's only like 10, which is quite nice actually. So then we're just gonna do a small summary. So if you want, you can just grab a piece of paper. So then you can have these ones by your side. This one is actually very useful. That's why I added it. So instead of a piece of paper, if you feel confident enough, you can just have this one screenshotted and you already know your alkyne reactions. But if you want a little bit extra notes, then we can do this as well. You have a separate sheet of paper and write them down. So first reaction. So we know that we can use NaNH2 as a strong base. If we have excess, we can use 2 equivalent or excess NaNH2 to create an alkyne from a dihalide. If we use NaNH2 with an alkyne, we can create an alkanite ion. So then, for example, we use two equivalents and we have two halogens, we can create a triple bond from it. And if we already have our alkyne and then we're using an H2, we can create an alkanite ion. Second reaction, catalytic hydrogenation. We can use H2PT to go from an alkyne to an alkane. We don't go to an alkene with H2P2. PT is a metal, therefore we can use other things like PD or Ni. Third reaction, catalytic hydrogenation. If you want to go from an alkyne to a cis alkene, you can use Poisson catalyst. A Poisson catalyst example can be, we can use Lindlards or Na2B. So these are some examples of Poisson catalysts. So Poisson catalysts, they produce cis alkenes. While on the fourth reaction, we're going to have catalytic hydrogenation. If you want to go from an alkyne to a transalkene, we're going to use NaNH3 liquid. So then NaNH3 liquid produces transalkenes. Okay, fifth reaction. So hydrohalogenation is similar to Markovnikov addition. If we add one equivalent of HX, we put halogen on the more substituted, but if treated with excess HS, we get two addition, putting two halogens on the same more substituted carbon. This is a thermomolecular reaction. The rate is K times alkyne times HS squared. So then meaning that if we have an alkyne, and then we have HS, only one equivalent, then our halogen is gonna go on the more substituted. But if we have excess, we're gonna have the two halogens on the more substituted side. Sixth reaction, addition of HBr with peroxides. So if we use peroxides with alkynes, we get an anti-addition. We add halogen on the least substituted part of the alkyne and hydrogen on the more substituted. If alkyne is terminal, the product is a mixture of E and C isomers. So you can see you have a terminal, like we said, HBr with ROR. Remember, peroxides, they normally represent anti-Markovnikov, so then we're going to add it to the opposite side. And then this is going to technically produce a mixture of E and C isomers. So in seventh reaction is a hydration of alkynes. If we treat an alkyne with H2SO4, H2HGSO4, we get a ketone as the product. So warning, alkyne needs to be terminal to get ketone. If not terminal, we get a mixture of ketones. So then remember, if it's in between, we can create a ketone from this side, and then we can create a ketone from this side. And if terminal, we can just create a ketone from the side that doesn't have a hydrogen. So then just from this side. That's why we only have one ketone instead of two. A reaction, halogenation of alkynes. Alkyne reacts with Br2 or chlorine 2 to get dihalide. If we use excess X squared, we get a tetrahalide. If we just one equivalent of X2, we get a mixture of products, the major product being a trans isomer. So then this is the same as when we did with alkenes. We're gonna add one halogen across a triple bond, and then another halogen across the other side of the triple bond. If we only get one equivalent, we're gonna get trans and cis, with trans being more the major product. But if we get excess, then we're gonna do the reaction like a lot of times, which is automatically gonna end up in tetrahalide. Non-reaction, osmolysis reaction. So there's no eraser method. Alkyne reacts with O3H2O. The product is two carboxylic acids. Unless it's a terminal alkyne, then your product will be a carbon dioxide. It's gonna be a carbon dioxide and a carboxylic acid. So then if it's not terminal, then if you want it, you can break it. We're gonna create carboxylic acids. And then if it's terminal, then we are gonna create a carboxylic acid, but then we are gonna create a carbon dioxide. So then 10 reaction. Remember that NH2 can be used to deprotonate a terminal alkyne. We can add an extra step and do an SN2 pathway on terminal alkyne to add an alkyl group. So this is what we recently did. NH2 is gonna add a strong base. It's gonna take a proton away from the triple bond carbon-carbon. Then with that we can add a new alkyl group across that triple bond. So here's a small look at chapter 10, radical reactions. So anion versus radical. So anion is their lumpers, while radicals is just shown as an unpaired electron. Radical reactions, they use single barbed curve arrows. They're also called fish hooks. So we just use fish hooks for radical reactions. Normal reactions, they use double barbed arrows or just the regular arrow you've been using. So then one more thing. So I don't want to scare you. So just one more thing before we end this video. The trans relationship are lower energy. It's technically what you know so far. Trans, they're lower energy. Cis relationship between radical and lumpers, they show higher energy, which automatically shows repulsion. And that's technically it, guys. So thank you so much for taking a little bit of your time to go over this with me, and I hope you have a wonderful day.